For a project at the TU Delft, we have to make a redesign based on the problems occurring in an existing building. We chose the EWI building in Delft. The building is situated on the campus of the Technical University of Delft and hosts the Faculty of Electrical Engineering, Mathematics and Computer Science. The building consists of two parts, a low-rise building along the Mekelweg and a high-rise part counting 22 floors. We focus on the high-rise part. A double skin facade is designed as a buffer zone around the building while maintaining the great view. First we show a quick analysis of the building in its context. Here you see a plan of part of the TU Delft campus. The sun comes up in the east, striking the east facade, turns south and eventually goes down on the west side. The most common wind direction is southwest. We did some research and found some problems with the indoor climate of the building. First of all, during summer, the sun hits the west facade for a long time and heats up the building, creating an unpleasant indoor climate. The double facade, which is supposed to work as a buffer zone, is not working properly and does not have operable windows. The interior is mechanically ventilated and completely separated from the outside air. Also, the mechanical ventilation does not allow for big audiences. There is no correlation between the amount of people in the room and the air supplied. How can we, in the high-rise part of the EWI building, reduce the use of energy used for climate issues in winter and summer while maintaining the view and creating a more adjustable indoor climate per room? We choose to redesign the west facade as many problems occur on this side. The sun and the wind mainly hit this facade, creating problems, but also opportunities. We searched for some examples, choosing the Eric Tower as our best reference. Foster and Partners designed a high-rise building in Düsseldorf, Germany. The building uses its double skin in a very smart way. The system they've used is a box shaft double skin facade. At one side of the double skin, openings are used to let in fresh air. In the adjacent shaft, air is heated by the sun, creating a natural updraft. Because of the extraction, the box stays cool and you are able to open the window. We use the principle of the Eric Tower in a redesign for EWI. In summer the sun heats up the shaft and creates a stack effect. The windows can be opened to gain fresh air. Because of the suction created by the stack effect, ventilation air is extracted. In winter, depending on the amount of people in the room, the box can be used as a buffer or can be opened for fresh air. Again, the shaft functions as an output for the ventilation air. To make the double facade work for each room, we made compartments in the facade. Each room has a double facade with an inlet for fresh air on the north side and the shaft for the extraction of air on the south side. In this way, each room is adjustable and can have their own indoor climate. When we look at the sun path, we see that the sun comes in and heats the rooms. Therefore, we shift the orientation, making it triangular, so the shaft gets heated but the box and the room stay cool. The sun enters the room in the late afternoon when people are leaving the building. We divide the EWI building in 3 compartments, so the stacking effect works on 3 levels at the same time. At the top of the shaft there is a heat exchanger that uses the heat created by the sun and transports it to the machine rooms on every 3 floors. The heat is converted and used for the central heating system in each room. The heat rises and is extracted through the shaft again. In this way we use heat recovery and the shaft doesn't only function as a buffer but also as a source of energy. This box shaft double skin facade can look something like this. A smart facade that creates an adjustable indoor climate per room and uses the sun as a source for energy.